The last technique we are going to see to improve the performance of neural networks is early stopping. The idea of early stopping is as follows. You stop the training when the validation error stops decreasing and you return the parameter values that correspond to the lowest validation error. Here is a plot of the evolution of the error through time computed on both the training and the validation set. Note that this curve is similar in shape to a previous one, but the x-axis is different. Previously, we looked at the dependence of the error on the model complexity, whereas here it depends on the number of epochs, the duration of the optimization procedure. Here you see that the error computed on the training set is decreasing when the number of epochs increases. This corresponds to overfitting. The neural network predicts well on the training set, but the performance are worse when computing on the validation set. The network does not generalize well. In early stopping, we monitor the validation curve during the training and stop the optimization procedure when the validation error stops decreasing. More precisely, in early stopping, the parameter of importance is the patience p, which is the number of steps you are willing to wait before the validation error decreases again. To put it differently, the algorithm stops if the last p evaluations are suboptimal in terms of validation errors. In this case, you choose the best parameter values so far, the one that minimize the validation error. You can also specify at which frequency you want to evaluate the model performance. Evaluating the performance at each iteration or epoch may be very costly and not very effective. Here is the code of the early stopping algorithm, which is nothing more than what I just mentioned. You have two different manners to use early stopping. The first one is described here and consists in using the optimal number of iterations found with early stopping. More specifically, you use a subpart of the dataset to determine the best number of iterations and then you train it on the whole dataset during the number of iterations you found. In this way, you make use of the full dataset to determine the best parameters. Another approach would be as follows. You train the algorithm on a subpart of the dataset in order to determine the best values theta star of the network parameters. You store the associated training error. Now you train the algorithm on the whole dataset starting at point theta star until the error of the training set reaches the error found in the first step. In short, in the first step, you have an idea of the training error corresponding to the moment you want to stop the procedure. You want to use this error in order to stop the algorithm when you run it on the whole dataset. In summary, in the first method, early stopping allows you to find the best number of iterations, whereas in the second method, you use the error on the training set to stop the algorithm. Early stopping is an old idea, but remains an active area of research. Several research papers are listed here if you want to know more about it. There exist other ways to reduce overfitting in neural networks by, for example, use soft weight sharing, as in CNN, averaging several models, we have seen that dropout is one possibility, or applying boosting, a type of sequential aggregation, to neural networks.